The cosmos of computer science is vast and ever-expanding. Amidst this digital expanse lies a fascinating realm known as artificial intelligence, or AI for short. AI embodies our ambition to create machines that can mimic and even surpass human intelligence. Like stars clustered in a galaxy, machine learning and deep learning shine as prominent constituents of AI. Delving deeper into the cosmos of AI, we encounter deep learning. This advanced subfield of machine learning draws inspiration from the intricate network of neurons in the human brain. Deep learning algorithms, known as artificial neural networks, consist of interconnected nodes arranged in layers. These networks process information in a hierarchical manner, much like our brains do, enabling them to tackle complex tasks. Imagine a child learning to identify different animals. By observing various features such as size, shape, color, and sound, the child gradually learns to distinguish a cat from a dog, a bird from a fish. Machine learning operates on a similar principle. It empowers computers to learn from data without being explicitly programmed for every possible scenario.
At its core, machine learning relies on algorithms. These algorithms act as sophisticated recipe books, guiding the computer on how to process and learn from data.
Let's consider a relatable example: email spam detection. A machine learning algorithm designed for this purpose can be trained on a massive dataset of emails, some marked as spam and others as legitimate. By analyzing various features within the emails, the algorithm learns to distinguish between the two categories.
The world of machine learning is brimming with a diverse array of algorithms, each with its own strengths and weaknesses. These algorithms can be broadly categorized into three main types: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning involves training an algorithm on a labeled dataset. This means that each data point in the dataset is tagged with the correct output or answer. The algorithm's task is to learn the mapping between the input features and the corresponding output labels. Once trained, the algorithm can then predict the output for new, unseen data. Unsupervised learning, on the other hand, is like an explorer venturing into uncharted territory. In this type of learning, the algorithm is presented with an unlabeled dataset, devoid of any predefined categories or outputs. The algorithm's challenge is to discover hidden patterns, structures, or relationships within the data without any external guidance. Reinforcement learning draws inspiration from how humans and animals learn through trial and error. In this approach, an algorithm interacts with an environment and learns to take actions that maximize a reward signal. Each of these machine learning algorithm types offers a unique approach to learning from data, catering to different types of problems and data characteristics.
Section 4. Deep Learning. The Rise of Neural Networks. Deep learning, a subfield of machine learning, has emerged as a transformative force in the realm of artificial intelligence. At its heart lie artificial neural networks, complex structures inspired by the interconnected neurons in the human brain. These networks, composed of layers of interconnected nodes, excel at processing vast amounts of data and extracting intricate patterns. Imagine a vast network of roads connecting different cities. Each city represents a node in the network, and the roads represent the connections between them. Information flows through this network, being processed and transformed at each node. Similarly, in a deep neural network, data flows through multiple layers, with each layer learning to detect increasingly complex features. This hierarchical learning process is what gives deep learning its power and versatility. In this section, we'll demystify deep learning architectures. These architectures are the blueprints that guide the design of neural networks, enabling them to solve specific tasks with high efficiency. One of the foundational architectures is the convolutional neural network, or CNN. CNNs are particularly effective for image-related tasks due to their ability to capture spatial hierarchies in data. They use convolutional layers to automatically and adaptively learn spatial hierarchies from input images. Another important architecture is the recurrent neural network, or RNN. RNNs are designed for sequential data, making them ideal for tasks such as language modeling and time series prediction. They have loops within their network that allow information to persist, effectively learning from previous inputs to inform future ones. Understanding these foundational architectures is key to leveraging the full potential of deep learning.
Now let's dive into a head-to-head comparison of different AI models. We'll examine their strengths, weaknesses, and ideal use cases.
First up, let's talk about traditional machine learning models. These models, like decision trees and support vector machines, are great for structured data and problems where interpretability is crucial.
On the other hand, deep learning models, such as neural networks, excel in handling unstructured data like images, audio, and text. They automate feature extraction, which can lead to higher accuracy, but often at the cost of interpretability.
Another key difference is in the training process. Traditional machine learning models typically require less computational power and time to train. In contrast, deep learning models often need significant computational resources and large data sets to achieve optimal performance.
As we look to the future, it's clear that AI will continue to shape our world in profound ways. From healthcare to transportation, the potential applications are virtually limitless.
And it's not just about the technology itself. The ethical considerations and societal impacts of AI are equally important. We need to ensure that AI is developed and deployed responsibly, with a focus on fairness, transparency, and accountability.
One exciting area of development is in personalized medicine. AI has the potential to revolutionize healthcare by providing tailored treatment plans based on an individual's unique genetic makeup and medical history.
In transportation, autonomous vehicles promise to make our roads safer and more efficient. By leveraging AI, these vehicles can navigate complex environments and make split-second decisions to avoid accidents.